Okay, good morning all of you. In today's session of class 12 physics, what we are going to do is that we are going to discuss the next concept in this chapter. The first concept we have discussed was Coulomb's law, and today we are going to discuss the next concept in this chapter, that is electric field. So basically what happens is that there is a charge capital Q, and at a distance small r from it there is a charge small q. So there is a charge capital Q, and at a distance small r from it there is a charge small q. Now the force on small q due to capital Q will be how much? Capital Q into small q by 4 pi epsilon naught r square. So this will be the force on small q due to capital Q. This will be the force. Now in this expression for force, if you put small q equal to 1, suppose in this expression if you put small q equal to 1, then whatever you get, that is called the electric field at, so let's give a name to this point. So suppose I call this point as P. So this is when I say E, okay, when I say E, that is the electric field at the point P. Okay, so if I use the symbol E, that is the electric field at the point P. Okay, so electric field at the point P, this is the symbol E, and this is Q by 4 pi epsilon naught r square. Now the mathematical explanation of electric field is this, but in physical terms there is a bit of a problem. Now before that, first let me tell you that why do we need electric field? Because we already have electric force thanks to Coulomb's law. So then why do we need electric field? What is the speciality of electric field? You see, what happens is that Coulomb's law has got one very obvious limitation, that you can only use Coulomb's law for a pair of charges. So if there are two charges, you can only use Coulomb's law for that pair. That's all. But if you are talking about electric field, then electric field is for a particular point in space. So Coulomb's law is for a pair of charges, electric field is for a particular point in space. So for that point in space, we can use electric field, right? So what happens is that the electric field, okay, it is more versatile than force, because it is for a point in space. So at that point, it gives you a complete idea of what is likely to happen if you place a charge at that point. Let me explain. Suppose if I tell you the electric field at point P is capital Q by 4 pi epsilon naught r square. Suppose I tell you this. Now I am saying that, so basically what did I do? I just took a 1 coulomb charge over here. I just took that here there is a 1 coulomb charge, okay, and I got this electric field. Now I am saying let me go back to that place and put a charge small q. Suppose I say that I'll go here and put a charge small q. So in that case, this is electric field E. Now I have decided to go to that place and put a charge q. As a result, that charge which I have put will experience a force. That force is F. So you get a vector relation F equal to QE. That means that if you know the electric field at a particular point, all you have to do is you put a charge over there and automatically you will get the force, and that's it. Whereas if you go by Coulomb's law, the problem is that over there might be so many charges in the neighborhood, you will have to consider the force due to each pair. And that's it. You cannot do anything more than that. In Coulomb's law, you have to only take a pair of charges. But if you say the electric field at the point P, then it's a little more generalized. So you decide later that, okay, I'll put a charge small q at the point P. So automatically the force on that small q will be force equal to QE. So this is the advantage F equal to QE. Now what happens is that this F equal to QE, this F equal to QE uh, is the vector relation between force and field. Now the issue is that as a mathematical explanation it is fine. So I consider that there is only one charge capital Q, and due to that charge I find the force on a 1 coulomb, that becomes a field. So as a mathematical definition it's okay. But from the physics point of view there appears to be a problem. You said we are saying that we'll put a 1 coulomb charge over there, but 1 coulomb is a very large amount of charge. You have to understand that the charge of an electron is 1.6 into 10 to the power minus 19 coulomb, and you are saying that over here you are putting a 1 coulomb. So 1 coulomb is a very large amount of charge. So physically it's not a very good approach. So physically the better approach is that you say like this, that let me see what is the force on a charge Q placed at the point P. There is a charge Q placed at the point P. So let me see what is the force on that charge Q. So the force is vector F. So force divided by the charge Q, provided charge Q is negligibly small, is the electric field at that point. So this is the actual definition of electric field. Mathematically, this definition is okay. So mathematically speaking, how will you define electric field mathematically? You will say it is the force on a unit positive charge placed at that point. Electric field at a point in space is a force acting on a unit positive charge placed at that point. Mathematically, that definition is good. But physically, it's not good, because you are saying that there is a 1 coulomb charge, and 1 coulomb is a very large amount of charge. So physically, the better definition is limit of the force acting on a charge Q divided by the charge Q as Q tends to 0, that will be the electric field. So physically this definition is better, because in this definition we are saying the charge Q is negligibly small, and therefore it will not disturb any charges in the vicinity. If you put a 1 coulomb charge over here, it will disturb all the charges in the vicinity. So this is the topic electric field, right? Now when you are doing a numerical of electric field, whenever you are doing any numerical of electric field, all you have to do is you just have to remember that the electric field is for a particular point. Number one. Number two, you may be using vectors. Like in Coulomb's law also there will be sums where you will have to use vectors. So for electric field also you may have to use vectors. That is number two. Number three, just keep in mind that ultimately the approach to solve a numerical of electric field and the approach to solve a numerical of Coulomb's law, the approach will be exactly the same. The only difference is that in electric field there will be one charge term less in the numerator. Approach will be the same, because vectorially they are related by just the fact that vector F is Q into E, right? So what we will do today in this session is that we will have a few homework questions on electric field, okay? And I'll give you the homework questions right now, and in the next session we will be doing something called properties of electric field. Properties of electric field we'll do in the next session. So I'll give you the homework questions now based on electric field. Okay, all of you, so these are the 4 homework questions from electric field. The first homework question, the electric force experienced by 10 to the power minus 6 coulomb is 1.5 into 10 to the power minus 3 Newton. Okay, the electric force experienced by 10 to the power minus 6 coulomb is 1.5 into 10 to the power minus 3 Newton. Find the magnitude of electric field at the charge. So there's a charge 10 to the power minus 6 coulomb. It is experiencing this force. You have to find the field where the place where the charge is there. Question number 2. Two particles A and B having charges 2 into 10 to the power minus 6 coulomb and minus 4 into 10 to the power minus 6 coulomb are held at 20 centimeter separation. So locate the point on AB where the electric field is 0. This is question number 2. Two particles A and B having charges this and this are held 20 centimeter apart. Locate the point on AB where the field is 0. Question number 3. A point charge produces an electric field of 5 Newton per coulomb at 40 centimeter. The question is, what is the magnitude of the point charge? And question number 4, you have 3 charges of 10 to the power minus 8 coulomb, 10 to the power minus 8 coulomb, 10 to the power minus 8 coulomb placed at the vertices of an equilateral triangle of side 20 centimeter each. So the question is, for this situation, find the electric field at the center. So 3 charges of 10 to the power minus 8 coulomb each at the vertices of an equilateral triangle of 20 centimeter each. Find the electric field at the center. So these are the 4 homework questions on electric field, and in the next session we will do properties of electric field. As usual, you will have to submit the homework by 9 p.m. of the next day, that is 9 p.m. Thursday. I'll end the session now. Bye all of you.